Hello everybody, this video is going to be about specific heat, which is a fancy way of talking about how much heat energy can something absorb. It's going to depend on the type of material that's being used. So the specific heat is the energy it takes to raise the temperature of 1 gram of something by 1 degree Celsius. So if we're talking about energy, then that's going to be a unit called joules. And we have mass, which will be in grams, and then Celsius. I know in the gas chapter, we like to use kelvins. We have to switch gears now, and we're going to be using Celsius for this thermodynamics chapter. It's very common to use Celsius because our thermometers come in Celsius, and so we're doing a lot of work with our thermometers in this chapter, so it's very convenient that we can just leave it in Celsius. So different materials can absorb different amounts of heat. So you will either be calculating the specific heat for a type of material, or maybe you'll look it up in a chart so that you can use that value. So the definition, if you look at it, we're imagining that we have a 1 gram sample, and we're going to put it, on a hot plate or under a Bunsen burner or something to give it some energy. And we're going to see how much energy it takes for that little tiny 1 gram piece of the substance to have its temperature go up 1 degree Celsius. And so they could have picked any size sample and any degrees, but to make it easy, we just use 1 gram and 1 degree Celsius. The equation for specific heat we call Q equals mcat. We call it that because the delta symbol here kind of looks like an A. So Q equals mcat. A lot of teachers will use a lowercase q. To be perfectly honest, I use an uppercase because I cannot write my lowercase q's nicely to save my life. They look like G's, and so it's a real problem. So I use an uppercase q. I personally don't care if you use uppercase or lowercase. So C we just learned is specific heat. We use a C to represent that. Q is going to be the energy that was either lost or gained. M is mass. And delta T is the change in temperature. Remember that delta means change. So you could rewrite this instead of putting delta T, you could actually substitute in that will be your final temperature minus whatever temperature you started at. We always do our ending minus our starting. If I were you, I would write down this bottom version of the equation as well. People have a tendency to forget how to go from delta to the actual individual temperatures, because sometimes we might be solving for the final temperature of something, or we might be solving for what temperature did it start at. So you do want to make sure you understand what delta T actually means. So one little trick that I like to show people is that if I gave you your temperature in kelvins for this chapter and for delta T calculations, you don't technically have to convert to Celsius. The reason for that is when you look at the size of 1 degree Kelvin versus the size of a degree Celsius, they're actually the same size increments. We're going up by the same amount of temperature each time. That's not true for Fahrenheit. Can you see how these are tinier measurements? A change of 1 degree here is not the same size as a change here or a change here. So if you're trying to do a delta T of 100 degrees, 100 degrees Celsius is going to be the same change as 100 Kelvin. So I'll kind of show you with some actual numbers. If you were to go from 30 Celsius to 50. When you do that subtraction, you get a change of 20 degrees. We've gone up 20 little increments of temperature, right? 20 degrees of an increase. If I were to convert those into Kelvin and then do my subtraction, do you see how it's still a change of 20 degrees? So my delta T number is not actually any different. And so it's not that you can always skip the conversion, right? There are going to be times where, you know, if you're talking about an individual temperature reading off a thermometer, you do need to do a conversion. But if you're talking about a change in temperature, a delta, as long as it's Celsius and Kelvins that you're working with, you can skip the subtraction. It's still going to give you the same delta value. If that's too hard for you to keep track of when you're allowed to and when you're not, then just always convert to Celsius for this chapter and then do it. You're just going to spend a little more time. It'll save you time if you can, you know, decide, oh, look, it's a delta. I'm going to leave it and just get my subtraction. All right, next thing I want to quickly go over is thinking about the plus or minus signs in these types of problems. The positive and negative values on our numbers this time are not always going to be told to you. Sometimes you have to decide if the number is going to be positive or negative before you do the question, because the positive and negative is going to relate to the direction of the energy, right? If it's gaining versus losing, we're going to have a different symbol. So if we're gaining heat, we're endothermic, remember. If we're losing heat, we're exothermic. If the system is absorbing energy, gaining heat, the Q value is going to be a positive number. Whereas if it's releasing energy to the surroundings, right, it's letting go of that energy, it's exothermic, our Q value will be negative. If you think about your equation, Q equals MCAT, well, in order for this to be positive, M and C are positive, so my delta T for endothermic is going to have to be positive as well, which makes sense because if we're gaining heat, if we're gaining energy, my temperature needs to go up, right? But if I'm losing heat, if I'm losing energy, then in order for Q to be negative, my delta T had to be negative, which makes sense because my temperature should be going down, right? Yes, the surroundings feel hot. Yes, if I were to reach out and touch it, I would feel hot. I might see flames or something, right? But if I were measuring the actual system, the temperature of the system would be decreasing. It's letting go of its energy. Okay, so let's go through some practice problems. These are mostly going to be little algebra problems. You're going to plug in your variables, you're going to isolate the missing one, and you have your answer. So a question might say something like this. How much heat is needed to raise the temperature of 10 grams of a substance from 40 degrees to 60 degrees if the specific heat is 3.8 joules per gram C? So what I can tell in this problem is that the substance needs 3.8 joules of energy to get 1 gram to go up by 1 degree Celsius. But I don't have 1 gram of substance. And I'm not going up by 1 degree Celsius, I'm going up by 20. So I'm going to have to plug my values in and figure out what the Q value here is, because I'm trying to solve for how much heat this is going to take. I have a mass, I have a delta T, right? I can find my delta T from these values, and I was told the specific heat. So take a minute, try to plug in your values to the equation up here, and try to solve for Q. So when I plug in all my values, you can see here grams are going to cancel on the bottom, Celsius will cancel from over here. It's totally fine if you put 20. I will say that when you're stuck and you're trying to find your mistake, it might be a little bit easier if you leave the subtraction in your work, at least at the beginning. I've noticed that that can make it a lot easier to find mistakes. But if you'd rather just put 20, I'm fine with that. So when I punch that out, you're going to see that the only variable left is joules, which makes sense because energy, Q, should be measured in joules. So it's going to take 760 joules of energy to get 10 grams of that material to have their temperature go up by 20 degrees. Once in a while, by the way, you might see kilojoules instead of joules. That's just a metric conversion. You might see kilograms or milligrams, just another metric conversion. In theory, instead of grams, I could give you moles and I could make you convert to grams first. So we could throw in some extra little things here and there. But for the most part, these specific heat questions are pretty much this easy. The algebra sometimes is a little tougher depending on what we're solving for. But you really are just plugging numbers in. All right, try this one. Try to figure out what you're solving for. List out what your variables are. So when I read through this question, I see, okay, I have 2 grams. That's going to be my mass. Oh, look, it told me some temperatures. That's going to give me a delta T. And oh, it absorbed 52 joules. That's going to be my Q value, isn't it? So this time what I'm solving for is actually C, specific heat. Now, if you remember, you don't have to convert these to Celsius. You can leave them because the subtraction will work out just fine. So I'm going to plug it in. I have 52 joules is mass times C times delta T. It's very common for your specific heats to be pretty small numbers, less than 1. Specific heat of water is 4.18, and that's really high for a specific heat. That's a lot of energy to absorb. So don't think you've done something wrong when you get little numbers like this. That's totally fine. Sometimes people are very, very bothered by the fact that I had Kelvin up here and then I put Celsius down here. But remember, that's just a little trick of my subtraction like I was talking about. Please don't get all worried about that. All right, try this one. If we look, I have 2 grams. The metal was heated from this temp to this temp, and it absorbed 52 joules. What's the specific heat? Now, one thing is, when you go to plug in these values, you're going to notice that we end up with a double negative because of this negative temperature. I see a ton of mistakes with these double negatives. So if you see here, I have my ending temperature minus my starting temperature, but my starting temperature was a minus. So when you subtract a negative, right, that's the same as a plus sign. Just be real careful about that. You solve for C and that's what you get. All right, let's try the next one. This time there's something a little bit tricky about the scenario that's happening. I want to caution you to think about what your positive or negative signs might be on some of the values. So why don't you try to list out what you think each variable would be? So when I read this problem, I say, okay, a 50-gram piece of metal, that's M, is put into cold water. Okay, so I've heated up this metal and now I'm dumping it in some cold water. And the metal is going to give the water 5,000 joules. That means it released 5,000 joules of energy. That chunk of metal let go of the energy. That means that there should be a minus sign here. My Q value should be a negative number, right? And that's something that the question may not put in there for you. I didn't type a minus sign here, did I? You have to supply the negative sign because that's showing that you understand the story of the problem and you understand which direction the heat is going. So when you say Q, it has to be negative 5,000, okay? Here's our specific heat, and this time we're actually solving for delta T. We're solving for our change in temperature. So Q, negative 5,000, equals MC delta T. Remember, releasing the heat makes Q negative. I would put some big giant note in your notebook about that, right? Big bright letters, arrows, stars, exclamation points, something. Now I'm going to isolate my missing variable and I find out that T is negative 16.67 degrees. That means that the temperature of the metal decreased by that much. Sometimes people will stop me here and say, oh, so does that mean the water went up by 16.67 degrees? And strangely, the answer is no. The water absorbed 5,000 joules, but the water has a different specific heat, so it can absorb the energy differently before the temperature goes up. So the metal temperature will decrease by 16 degrees, but the water is probably not going to go up by that much. It'll go up by a smaller amount because it can hold on to more energy before the temp goes up. So we will actually have an entire lesson called calorimetry, where we learn, okay, if the metal goes up or down by this much, how much will the water go up and down by? And so that will be its own little lesson. Okay, we'll do a lab about that as well. All right, the next question, oops, wrong direction. The next question is going to be a little bit more challenging from an algebra standpoint, okay? You're going to need to be isolating a variable that's a little bit more algebra intensive. And I honestly do not care how you go about isolating that variable. If you are the kind of person that likes to isolate your variable while it's still in an equation form before you plug in your numbers, great. If you would rather plug in your numbers and then isolate it like I do, great. If you like to simplify everything down and distribute it and then solve, great. If you like to kind of wait and move everything around and do your distributions at the end, great. It really doesn't matter. We will get the same answer. So I'll show you a couple different ways that people tend to solve this problem from an algebra standpoint, and it really doesn't matter which way you do it. Okay, so let's find our variables. We have a 25-gram piece of metal. This time it's cold metal and it's put into hot water. The metal absorbs 154 joules, so Q is going to be positive this time, right? The specific heat is 0.35. Look, it does not want a delta T. Do you notice that? It told you what temperature you ended at. And look what it's actually asking you for. It's not asking for the change in temperature, it's asking for the initial temperature. So you're going to have to solve for TI, for T initial or T starting, whatever you want to call that, okay? So setting up our work is going to be a little bit different because instead of having a delta T value, we're actually going to go back to that more specific equation where delta T is TF minus TI. Be really careful on these problems. I see a lot of silly algebra mistakes. It always feels bad to get a problem wrong because of algebra, right? But if it's wrong, it's wrong. It's just something you have to understand, right? One of the things we are assessing you on is, can you manipulate your equation, which is involving the algebra. So I have my Q value, which is positive because it's absorbing energy. I have my mass. I have my specific heat. I have my ending temperature minus my initial temperature. Because remember, delta T is TF minus TI. Now comes the choose your own adventure in terms of your algebra, okay? So I don't care how you want to isolate that missing variable. I don't care what order of operations you take to get T initial, just get that number. So pause here, do whatever version of algebra you're going to do, and we'll see how it goes. We'll see if you get the correct answer. All right, so I personally divide both sides by 25. I divide both sides by 0.35. I just like to move all the junk to the other side. Now I'm going to end up flipping it, right? I'm going to put TI on this side. I'm going to subtract all the junk from this side. And I end up with 7.4 degrees Celsius. If that's not the order you did your algebra, who cares? So just to give you a couple of variations, I just took pictures of doing it on the whiteboard one year. Everybody wanted to see a different way of doing it, and so I did a couple different ways. So some people like to multiply this out and then distribute it. That seems to be a popular way. Great. I hate distributing. I don't know what it is about me. I just hate it. Right? So I tend not to do this way, but you could if you wanted. You'll get the same answer, see? You could simplify as you go. So you could do kind of what I did and move all the junk to the other side, but then you could simplify it, and then you could start isolating your I a little bit more. It doesn't matter. You get the same number, right? Sometimes people will say, could I solve for delta T first and then do a second equation? Once I know what delta T is, then could I solve for Ti by plugging it into final minus initial? And I will say that yes, that works for a simple specific heat problem. That's okay for a problem like this. However, that's not going to work for calorimetry problems. In a calorimetry problem, we are going to have to leave it as T final minus T initial plugged into the original equation, or we have some issues. So if you do it this way, you're just going to have to be careful that when we get to the calorimetry lesson, you pay a little more attention to what we're doing. I just see some issues with people who do it this way, that their algebra doesn't get the practice it needs for when we have these calorimetry problems. So as always, my suggestions are just based on doing this for 13 years, right? I'm just trying to give you tips on where I see people make mistakes, where I see problems show up, where I see people struggle. I'm not saying you can't do it this way, just be a little bit careful, okay? All right, everybody, that's it. I hope that was helpful. Bye.